Hello, it's Ryan. This is our third example using Coulomb's law. It's about more point charges. In this example, you're given 3 point charges with charges and positions listed below. Determine the net electric force on Q2. And then they go ahead and give us the charge and the position of each charged particle. So something to keep in mind here is that you'll definitely need a picture for this, but you get to create your own coordinate system, so I would be careful. I wouldn't just throw your coordinates in there willy-nilly. Like, what I mean is I wouldn't go 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 1, 2, 3. Like, that's not really going to help when you're trying to figure out if maybe you did it right or wrong. You know what I mean? So what I'm going to do is just take a little bit more care in drawing this, but not much. You'll see. Still start with our regular coordinate system, and we'll just go up somewhat of regular intervals. So they don't have to be perfect. And honestly, I'm probably making too many, but so that's plenty. This is our x in meters and our y-axis in meters. These were defined in a two-dimensional coordinate system. So let's give them colors. So let's say Q1 is this one. So Q1 is at 0, so we go over 0 and up 1. So there's Q1. Let's give Q2 orange. Q2 is 3 over and up 0. There's Q2, and that's the one we're interested in, calculating the net force. And let's make Q3 blue, and that would be -2, 0. And so actually, I'm going to zoom in a little because we have the ability to do that nowadays. And I'm going to add a little bit to these pictures. So I'm going to show that right here, that is the distance r between 2 and 3. And right here is the distance r between 1 and 2. And I could show the distance between 1 and 3, but I don't think we're interested in that because we're asked specifically about Q2. So I don't want to spend too much extra time. Something else then that we can show from just what we're given here is then we know R2, 3, well, that's just 1, 2, 3, 4, 5, 6 meters, isn't it? Sorry, bad math. It's 5. Hope you caught me. 5 meters. We know that R1, 2 is, so it looks like we'll have to do a little Pythagorean theorem, won't we? We have something that is a right triangle. The hypotenuse of the triangle is what we're looking for. And so it'd be 1 squared plus 1, 2, 3 squared. So that would be the square root of 10 because c squared equals those squares added together. Anyway, the point is root 10 meters will be R12. So the other thing that I think is important to do, well, let's do it separate from our picture. I don't want to clutter this up. So we'll zoom back out. Now we should show a free body diagram of Q2 because that's the one we're interested in, the net or total force that is acting on it. Q2 will just be a cute little point charge like that. Now, another thing we could note is that Q2 in our givens was negative, and these were both positive, weren't they? And so what we're going to do, which actually is an idea we've been using since Physics 1, is we're going to analyze our forces independently of each other. I'm going to look at the effects on Q2 due to the first charge, Q1, So there will be an attractive force on Q2 due to Q1 because they're opposite charges. And then separately, I'm going to look at the force due to Q3 on Q2, which is also going to be attractive, isn't it? But we'll also know probably that the first force on Q2 might be a little bigger than the force on Q2 from Q3 because it's farther away. And I think the forces are a little bit, Q3 is very small also. Anyway, I don't want to bog you down. So I'm going to show each of those forces. So the force on Q2 due to Q1 is attractive, and so it'll look something like that. I'm actually going to make it even longer. That's Fe from Q1. And then the second force on this will be attractive and smaller, Fe from Q3. So I'm also going to go ahead and put a coordinate system in here, an XY coordinate system. And this time I didn't flip around my positives and negatives because it'll make sense to have positive going to the right and negative going to the left because of our picture having a standard coordinate system in it. We could flip everything around as long as it all makes sense in our pictures, but I think it would add a few extra steps and thought processes to our work that are unnecessary. So this is a good FBD. We could also, at least right now, take a guess that this is probably going to start to accelerate, but we don't care about that. We're talking about electrostatics, and so we're looking at just the net force on something. We're not asking you at all about how the body responds to that net force. So the FBD is really just to help us keep track of what we're adding together. We know that the net force, F net, on our Q2 will equal Fe1 plus Fe3 from our picture. That's in general. Now, the way that we've been doing this since Physics 1 is we would look at components of these forces. We would say the sum of the forces in the x direction and add those together, and the sum of the forces in the y direction, and then those together would give us F net. So one way to think about this, F net, is equal to, it would be the sum of the forces in the x direction, and we would indicate that that's in the x direction, plus whatever the sum of the forces in the y direction are in the y direction. So this is one way we could get the answer completely mathematically. A different thought process might be to diagrammatically add these forces together. You could take Fe1 and add it to Fe3. Oh, I did it in green. And then you can tell when you add these tip to tail. So I'll actually do our resultant in red. This would be F net. And as you can see, the total force has a horizontal component and a vertical component. F net in the y direction and F net in the x direction. And then from this picture, we could also show then that the y direction and the x direction of our first force, Fe1x, Fe1y. Can you see the correlation? It's this net force is really just the x components added together, and this net force is just the y components, which one of them is 0 in this case, added together. And that's where another way to derive this rote mathematical definition. So there's a lot of different thought processes you can use to think about this. From our picture, though, we can, I like this the best, so I'm going to use this. We know then that F net is equal to, we will have FE1 in the x direction plus FE3, and that's going to be in the x direction. And really, it's going to be in the negative x direction, isn't it? So I'm going to put that in now. And then we have our y direction, so we'll add the F net y, which is just FE1 in the y direction. I'm going to be redundant here and say plus 0 in the y direction, and that 0 corresponds to FE3 being horizontal, so there's no vertical component. So it looks like for FE3 we don't need to worry about any angles, it's just going to be a regular Coulomb law, but it looks like for FE1 we have an angle here. And so we're going to have to use a little bit of trig to get through this. We're going to know this angle here from our picture, aren't we? That angle there, theta, we can use the inverse tangent of 1 opposite over 3 adjacent. And so we could have done that when we were calculating our radii. I'm just going to show that here. Theta from this right triangle. So tan theta is equal to 1 meter over 3 meters. And so theta is equal to the inverse tangent of 1 over 3. And if you were to calculate that out, I believe you'll get something like 18 degrees, something like that. 18.4 maybe. 18.4, that's it. 18.4 degrees. And so we can see then from our FBD that 18.4 degrees is here. And so if we use cosine of that, we'll get the x component. And if we use sine of that, we'll get the y component. Okay, so F net is equal to, we have negative. So this is a little long. If you wanted to go ahead and calculate each of these before substituting all these in, you could do that. I just like to show everything since I'm the teacher, I guess. So we have negative in front because we know these are going to be in the negative x direction in the end. So we have k. And k is actually going to be in both of those terms. I'm going to write everything out and then simplify. So we have k. Fe1 would be the force between 1 and 2. So we have Q1 and Q2 over R12 squared. And that's going to be the x component, which we said was cosine of theta, plus the Fe3 is not on an angle at all, so we don't have to worry about thetas. So we have k Q2 Q3 over R23 squared. That's Fe3, and that's in the x direction. And we're going to add in the y direction, we have Fey, we have sine theta, and it's the force between 1 and 2 still. So we have Q1, Q2 over R12 squared, but now we're looking at the y component, which was opposite, so we have sine theta in the y direction. And so now it's just a whole bunch of plugging in. If you wanted to simplify some of your calculations, you could factor common things out. So like in here, for example, I guess you can't do anything here, it's one term, but you could rewrite this one as negative k q2 in front, and then you could have the q1 cos theta over r12 squared plus q3 over r23 squared. So you'd have a little less to calculate or to type into your calculator, but either way, it's kind of a long calculation for your calculator, and in the end, when you get through it, you know the net electric force on Q2 will be equal to, and you'll get negative 57 nanonewtons in the x direction, plus 17.9 nanonewtons in the y direction. And recall, nano is nanonewton rather is 10 to the negative 9 newtons. So just to remind you, nano is 10 to the negative 9. If you were to calculate this, oh, you know what? I might have made a mistake. I think that this is probably wrong. I did that in my head, but I think that might be for our final answer. So this is not wrong. This is all good. All good. I just don't know if I calculated that right. So all this is good. All this is good. This is good. This was calculated with the right answer. So don't worry about any, there's no other mistake. I just don't think that this theta here was calculated correctly. But the method was correct. I just did it too quick. Anyway, if you wanted to answer this with an angle instead of using vector notation, you could say F net was equal to, and if you calculate this all out, you'll end up with 60 nanonewtons at 161.6 degrees. So this is the same answer. But that's a little bit of a more challenging problem using Coulomb's law, and it's just challenging because it took a little bit more organization to calculate it. It's actually something you're quite used to, adding forces like this. I just took the liberty of showing you a couple different ways to think about it and the final answer you should get to. Good luck studying.